Hello, my name's John Watson. I've been working on building things for space for my whole career, and I still do work. This started in 1968, so that's 52 years and counting. I did a degree in physics and then went into one of the big engineering companies. And it was just at the time when space was emerging as a new area of work, and the people were thinking of using it for communication systems, navigation systems, and so on. And I spent probably most of that time working in Stevenage for the various companies that eventually merged and became Airbus. To get anything into space, you need a rocket. The thing on the right, I photographed at the test site in the eastern part of Germany called Peenemünde, where the V2 rocket was developed as a means of dropping large bombs onto London. But it was the first object to leave the Earth's atmosphere. And the engineers who'd worked on V2, a lot of them were encouraged or taken to America at the end of the war, where they worked on the American space program. The thing in the middle is one of the remaining Saturn V rockets. And this is the largest rocket that has been built to date, although there are some bigger ones coming. And this is the thing that was used to get the men to the moon in the 1960s. On the left is one of the latest things in rocketry, which is a rocket that's done its work, and then instead of crashing into the sea, it's been flown back to Earth to land on legs. This is a very clever piece of automation, and it can make launches much cheaper, so that the stuff you've built is not thrown away but refurbished, refilled with fuel, and launched over and over again. And since those early days, there are a lot of man-made objects up there. It looks crowded, but remember, this is a cube which is about 100,000 kilometers across. So there's lots of space up there, but we still have to be careful. There have been collisions, and if you have a collision, it can generate more debris and lead to other collisions. So we are very careful. The prominent circle happens to be around the equator. Now, there's a very good reason for this. It was pointed out by the writer Arthur C. Clarke back in the 50s. If you put a satellite not far above the Earth, it goes round in about 90 minutes. If you put an object about the distance of the moon, it takes a month. And if you put it at the distance of this circle, it goes around in 24 hours. And as long as it's rotating in the same direction as the Earth, it seems to be stationary. And that's a very useful position for satellites that are doing communications between 2 points on Earth, because it stays in the same place and you don't have to change to another satellite. Now, I did most of my work on communication satellites, and this is a typical early one. It's quite big. It's the size of a small delivery van, maybe 3 meters in each direction and about 4 meters long. You can see white paint, and white paint is for the surfaces that reflect radio waves down to the earth, and it's white in order to reflect as much of the sun's energy as possible. The gold colours are blanket material to reflect away the sun's heat and try and stop the objects getting too hot. If we look at an image of what a typical satellite will look like in orbit, this is a more modern satellite that's rather bigger. We can now see a third type of colour. On the sides of the box are mirrors, and those are there to radiate away heat. We can now see the solar array that generates the power to run all the equipment on the satellite. And the objects that stick out away from us on the end of deployed arms are thrusters. They're kept well away from the satellite so that the exhaust from the thruster, which is used to push the satellite into the correct place and keep it there, doesn't hit the delicate surfaces of either the reflectors that reflect radio or the solar arrays that generate the power. Things can go wrong. The left-hand image is an explosion of the rocket carrying the first satellite I worked on in any great detail, and that blew up on launch in 1977. Interestingly, some of the equipment was recovered from the sea, and it still worked. It's made to be very robust. One on the right is the Space Shuttle Challenger blowing up in 1986. And that was more upsetting for the engineers because that was a mission with people on board. So we take a lot of effort to stop things going wrong. You have to test, you have to design well, you have to review your testing and your design. Of course, normally things do last a long time. Although our launch failed in 1977, two of the other satellites that were launched in 1977 were the Voyagers. And those Voyagers were launched in 77 and they are still working. And on their routes, they visited Jupiter, Saturn, Uranus and Neptune, sent back photographs and other data. And they're still in contact with those over 30 years, over 40 years later. So these are pictures of the places we go to do testing. Chap in his somewhat 1970s haircut is looking at test results. The top picture is a satellite in what we call an anechoic chamber, where it's being used to check out the antennas. At the bottom, a satellite is about to be moved into a vacuum chamber so that it can be exposed to vacuum and high and low temperatures to check that everything is working correctly. And we use satellites for lots of different things. The examples I've shown were to do with communicating between places on Earth, and that is very important. This is a science satellite. This is a satellite that was basically looking at Earth. Lots of instruments to detect things about the Earth, to measure temperatures, look at ice cover, look at clouds, and do other measurements of the Earth's environment. Of course, satellites are used for navigation purposes. Everyone who uses satellite navigation now relies on that enormously. And it's not just for navigation, that's also the method of delivering time. And we then have science satellites looking out from the Earth's environment. If you put a telescope outside the atmosphere, it can see more clearly, but it can also see in frequencies that aren't visible from the Earth. So you can look in X-rays, you can look at infrared. And the military have very large numbers of satellites for numerous different purposes. So there are lots and lots of different types of system. The projects that build these are often very large. So it may take maybe 10 years from initial concepts, discussion on whether this is a good idea, finding ways to raise the money, doing detailed design. And by the time the engineering work is in full swing, you may have hundreds of people. These are people with a very wide range of skills. There are managers, there are people who analyze things, there are people who test things, and there are people who think about how a system will work, how it will be controlled, and in the case of commercial satellites, how you will get your money back. And periodically, in one's working life, you get the opportunity to see a launch, which is something quite exciting, but it doesn't happen for many people. I took these photos, so watching one of the satellites I've done a lot of the system design on in the 2015 era. And on the right, and as we come to the end, some rather nice pictures of the Earth from space. One is from those early Apollo missions. It's the view of the Earth rising above the moon as the orbiter round the moon comes round. And the picture on the right is a picture from a satellite that's gone a lot further away from Earth than the moon, and that is the moon crossing the Earth's disk. So I hope that was interesting. I've had a very interesting career designing things and watching them come to fruition. It's very satisfying when the thing you've designed gets up there and then works. And it may be a long time after you did that initial design, but it's still very satisfying. So thanks for listening. I hope that was interesting, and